Hey class, let's talk about voltage. This is the next PowerPoint. It is section 5.2. It is getting into resistance, but in order to understand resistance, we need to have a better understanding of current and of voltage, which we could kind of break into two parts. So if we were in the classroom, we would be able to do this fun demonstration where half of you would be on one side of the class, half of you would be on the other, happy with paper, sad without paper, and we would have this Bunsen burner in the middle. So I would be the electric supply, the cell. A battery is a bunch of cells together, but when we just see our cathode and anode like this, it is called a cell, and the cell is providing each of the carriers, which are you, the students, or the electrons, with energy. So the paper you're holding is your energy, and as you leave the cell, or this power source, this energy supply, you have this piece of paper which signifies energy, and you're going to carry that, right? You're going to move along with some speed or electron drift speed until you reach this lamp or this Bunsen burner or whatever it is in our circuit that is drawing the energy. So it could be a lamp, right? It could be your cell phone, whatever it is that is consuming the energy from your energy supply. So the electron will carry the energy to this, we'll call it a lamp here, and it'll burn up the energy. It'll consume the energy, and the electrons will leave without energy. So sad electrons, sad students without their paper, without their energy. So we have the cell, that's me, the teacher, handing you little slips of paper as you walk around the room. When you have the paper, you are energized electrons. When the Bunsen burner burns up your paper, you are de-energized electrons. And you'll continue walking through this circuit, right, until I stop giving you paper, and that would mean the lamp is turned off. There's Eleanor electron. So a coulomb of charge. This is just getting into the idea of what 1 coulomb of charge really represents. We've talked about coulombs a little bit in the last 2 lessons, but this just gives you an idea of the scale. So a coulomb is the charge that, wow, I didn't even count the zeros here. 5, we'll call it bazillion electrons have. So that's 3, 6, 9, 12, 15, 18. 5 times 10 to the 8. Wow. 18. Big number. So we need more than, it's about, yeah, I don't even have the prefix for that one. Not quite a Googleplex. That's 100 zeros. But we have 18 zeros. That's how many electrons it takes to make up 1 coulomb. So we need to have billions upon billions of electrons for 1 coulomb of charge. So a coulomb is a lot of charge, or you could think of it the other way. An electron has hardly any charge, right? The elementary charge is 1.6 times 10 to the negative 19 coulombs, which is an extremely small number. So here's our first piece that we need to really understand. We did talk about it a little bit with electron drift speed, but current is an essential part to understanding resistance. So current is measured using an ammeter. That's what this A is here. A stands for ammeter. Ammeter. And an ammeter will tell you how many coulombs a circuit has, which is essentially counting how many electrons, how many coulombs of electrons go past every second. So even if you are working with a microcoulomb, you're still having billions of electrons go by each second, because remember, a coulomb is that 5.26 times 10 to the 18 ginormous number. So current, whenever we're thinking about current, we have coulombs per second. So the flow rate, how many are going by, right? So how many of these electrons are passing by with their charge, their energy, per unit time. So we'll measure that in coulombs per second, past a set point, which in this case would be our ammeter. Right, so 1 amp is a coulomb per second. Ammeter measures amps, which is our standard unit for current, which is coulombs from our current per second from the time it takes, the time that we're measuring them passing. All right, that is current. We're not going to do that practical because we don't all have voltmeters at home, unfortunately. So we're getting into some of the complicated math stuff, diagram stuff, understanding stuff. Here's our most simple circuit we're going to look at. We just have a circuit with a couple of these resistors that are in series, we call it. So if we just have one path for the electrons to pass through, that is what we call in series, because it has to pass through each component one after the other in a very specific series, right? We'll have an electron leaving the negative repelled away, right? And this is how fast, or I guess how much charge is passing each point per second in coulombs per second. And that'll be the same at any point in the circuit when we have this simple one path series circuit. Not all circuits are that simple, unfortunately. We also have what we call a parallel circuit. So here you can see we have two parts of the circuit running parallel to each other. So instead of all of the electrons just going on this one path, we're actually going to split the current between our two parallel paths. But it's important to understand that we need to have the same current going in as coming out. So we have 2.5 amps leaving this intersection here, and we have again 2.5 coming in. So what's going into this parallel component of the circuit needs to equal what is coming out. So even though half of the electrons will flow here and the other half will flow here, when we join back up, we have the full amount of the electrons returning to our cell. So even though the current splits, we can't create or destroy charge, right? And by extension, we can't create or destroy current because current is charge per second. So in this isolated circuit, since charge can't be created or destroyed, our total current needs to stay the same. So what goes into our cell must equal what goes out of the cell. So parallel circuits do get more confusing, and that's because we're having our flow splitting at these ever important intersections. All right, those intersections are important because we use them in what is known as Kirchhoff's first law. You'll spend lots of time working on questions around Kirchhoff and his laws. This first one, just really simply put, I already summarized it on the last slide, but the total current flowing into a junction, right? So this would be current I1 and current I2 needs to equal all of the current that's flowing out of that junction. So I1 and I2 are in, they're on one side of our equation, and we have these other three streams or paths for our electrons or a current to flow, I3, I4, I5. But we know that those three streams added together need to equal the two streams that go in, because the total current that's flowing into our junction, this, think of it like, I don't know, an intersection or a railway junction. What goes in is the same value amp-wise, current-wise, as what's coming out. So we need to again have conservation of charge. So if you look at any intersection on any circuit, right, we'll be able to sum the current in, and it must be always, every single time, equal to what comes out, according to Kirchhoff's first law. Okay, so this law is all about current, all about the flow of electrons and the charge passing a point per second. So the sum of all current must equal 0 into a junction. All right, and this depends on what reference system we work on. If we say into a junction is positive and out of is negative, right, they need to equal each other there, right? So into would be a positive and out would be negative. That's just a nice, simple way to think about it. So if we have our intersection, our junction here with 10 flowing in, and we have 5 and 5 flowing out, this summation would, for Kirchhoff's first law, sum of all current, we would have positive 10 from our 10 amps flowing in, and we're going to have to subtract what's flowing out, our negative 5 and 5 would equal 0. And that'll always be true. You could switch around positive and negative, but essentially this is our mathematical expression of what current flows into a junction needs to equal the current flowing out. Okay, so Kirchhoff's first law is all about current. Now we're going to look at another essential piece to our resistance and our circuits, which is voltage or electromotive force. So you're going to hear the IB switch between these two descriptions of voltage, EMF, which they abbreviate with that symbol, and which is expanded, the full word for it is electromotive force. I don't want to write that too much. Elmo force. There we go. Now you will never forget. Elmo force, electromotive, so we're moving electrons, force. And I'll get into the difference between electromotive force and potential difference. Both are measured in volts, and they are very close to being the same. There is just some small differences between them that the IB likes to be stickler about. So when we're measuring voltage in this electromotive force, we're essentially checking the difference in energy between 2 points. Here, those 2 points happen to be right after the cell and right before the cell. So the difference in energy is obvious because these electrons are carrying these pieces of paper that resemble or symbolize energy. So we have high energy as they leave the cell, and we have low energy as they're coming back after being consumed by the lamp or the Bunsen burner. So whenever we're talking about voltage, we're talking about a difference in energy between 2 points of our circuit, right? So it's the difference in energy per coulomb. So a volt is always change in energy per coulomb, or per current. No, sorry, charge. We would write that as Q, I think. Yes. So the change in energy per coulomb, right? So those units will always be joules per coulomb, which we've talked about in a previous one, right? 1 volt is 1 joule per coulomb, and that's what we just focus on when we're thinking about these electromotive forces. Okay, so electromotive force is between, or that's one way to think about it, I guess. The difference between the cell, and it would be present even if there was no current flowing, because the cell is providing this electrical potential difference between our cathode and anode, our negative side of the cell and our positive cell. We're going to have an energy difference between there. Whereas voltage, in terms of potential difference, that's what we're talking about when we see PD. That's our potential difference. We're now looking at something other than our power supply or cell. We're looking at the potential difference somewhere inside of our circuit, like in this case before and after the lamp. Again, still measured in a joule because it's still an energy difference, right? A change in energy per coulomb. But now we're before and after a lamp instead of before and after our cell. So one of the big differences is with electromotive force, even if there's a break in the circuit and we don't have any current flowing at that point in time, there still will be an energy difference. Whereas with potential difference, we need to have this electron flow, right? If nothing is flowing into it, right, we're actually not going to have any voltage or any energy difference before and after. So if that still needs clarifying, you can do some deeper digging, ask me for some extra explanation, but try not to get too hung up on the difference. They're both measured in volts. They're both essentially voltage, just with some minor differences about where you're measuring that voltage and whether or not current or flow of our electrons is necessary to measure them. All right, so just like with current, things are a little bit easier when we're looking at things in series. So here's our rule for a nice series circuit, which means we only have a single path. Everything is going to affect each electron in series, one after the other, which is why we call it a series circuit. So just like our current, each electron has to flow through each of these resistors or lamps or whatever it is in that drawn up diagram, circuit diagram. So for voltage, the sum of the potential differences, so again we're looking at a point before and after each lamp rather than before and after the cell, because that's electromotive force. But the sum of all the potential differences across all three lamps needs to equal the electromotive force across the cell, or cells if you have more than one. So our voltage supplied by the cell needs to equal the potential difference across each lamp. And complicate things again, this one is super crazy. In a parallel circuit, the potential difference across each lamp is equal to the electromotive force across the cell. So if we have our lamps or our resistors running parallel to each other, they're actually going to have the full change in energy across each of them. They're not going to have the same current, right? Each of these will have less current flowing through them, but they will have the full voltage. And we can use this phenomenon to create some pretty powerful circuits, right? And this is just one of those laws and one of those rules in electric circuits that we just need to keep in mind, because it doesn't necessarily intuitively make sense. It's something that we need to pay careful attention to and almost memorize. But the potential difference across each lamp that is in parallel will be equal to the voltage of the cell. So each lamp is receiving the full voltage, but only a portion of the current. Whereas here, each lamp is receiving the full current, but only a portion of the voltage. And when we're thinking about these voltages rather than these currents, we're now thinking about Kirchhoff's second law, right? So this has to do with our voltage, not our current. So that's kind of how you can keep it straight. We're looking at current, we're thinking about our intersections, our junctions, and the current flowing in and out. Second law, we're looking at voltage, and now we're using loops. So what that loop really means is, as an electron flows through this circuit, we have this loop that it's going to travel in. But that's just the general loop that each electron will travel. Within this general, this general guy, I think I'm going to overcomplicate this way, go too far into it, but let's say these are the lamps that we saw before, right? Our circles with the X's through them. The potential difference across each lamp needs to equal the potential difference of the electromotive force of our cell, right? We already know that from before, but now we're using this idea of a closed loop, and the sum of the EMFs, right? So this would be our electromotive force from our cell in any closed loop needs to be equivalent to the sum of the potential drops. So we have these three guys that are dropping our potential. They're somehow consuming the energy. They're lowering the energy at each point. And we know that we can't create or destroy energy, just like we can't create or destroy charge. So the energy that's leaving the cell needs to be equal to the energy that's dropped and returning to it. Okay, so Kirchhoff's second law is this idea of an electron traveling on this loop. It starts with a set amount of energy from the cell, which is its electromotive force, and it's being dropped as it runs through each of these components, these lamps, these resistors, whatever they might be, right? We're having a loss in energy at each of them, and that loss in energy needs to be equal to the energy provided by the cell. Right, and here's where this idea of loops becomes important when we have more complicated cells or circuits where we have multiple cells, multiple loops. So this 10 volt cell means that within this closed loop, we need to have resistance adding up to 10 volts. And in order to actually do that, we need to learn about resistance, right? Sorry, the 10 volts supplied here has to equal the 10 volt drop across each component, each resistor. So we have really 3 loops here. We have this first guy, right, supplied by just this single cell. We have the second guy supplied by cell 2, 20 volts. And then we have an overall loop, right, that's running instead of through this R3, resistor 3, it's passing through R1 and R2 and both of our cells all the way around. I guess I'll just point this out now because it's going to become very important later. When you're drawing in your loops, you have to make sure that you're not drawing them conflicting with each other or battling against each other. They always need to be in the same direction at the same component of the circuit, which can be a little bit of a difficulty starting out. What I mean is when we're looking at circuit 1 here, or loop 1, right, it's going to have electrons come here, travel down, come back. Now with loop 2, if I were to draw it instead of as it's shown here, if I were to draw it like this, with the electrons coming down, coming up here, we're going to have the electrons battling it out, right? Because from loop 1, we would have them coming down. From loop 2, they would be fighting against each other going up. And we don't want that. We want the electrons to all flow in the same direction, right? And that's why this loop is drawn with this counterclockwise direction so that the electrons are flowing to the left here and then down here. And where that gets a little bit convoluted and backwards is with this overall loop. But even so, right, these components in the middle you're going to usually want. It depends on the sign convention you use as well. That'll make more sense later, right? Because this third loop is actually in the opposite direction of the second loop, right? And when they are going opposite to each other, you'll just have to subtract them from one another, right? But most often you'll see that you'll try to keep your loops such that anything inside is flowing in the same direction. Okay, we'll make more sense of this later for sure, once we actually learn about resistance, how to calculate it, and how to use both Ohm's first and second laws to calculate any unknown current or any unknown voltage or any unknown resistance. Right, so we need to first talk about resistance and power, but this is just a quick recap of what we did today with our first and second Kirchhoff law. First with current flowing into a junction, second with voltage flowing in a loop. Okay, and I did say there would be some explanation of the difference between potential difference and electromotive force. Here's all you really need to know, and again, don't spend tons of time pulling hairs over this. This is just one of the weird little intricacies of the curriculum that you do need to have some awareness of. So a potential difference is between 2 points where work is being done, right? So the electric potential difference between any 2 points, we were looking at points before and after a lamp or a resistor, right? So we have 2 points, point 1 and 2. The electrical potential difference between those 2 points is equal to the work done per unit charge to move a small positive test charge between those 2 points. So if I took this positive test charge, right, with probably the elementary charge plus 1, and I had to move it across between those 2 points, some distance, right, I'm going to need to apply a force to push this guy against the flow. So a force over some distance, that'll be my electric force over a distance. And when I multiply force times distance, I'll get my work. And the work per charge is equal to the potential difference. Right, so in order for that to happen, we need to actually have some current flowing through, carrying energy, right, so that we can come up with this positive test charge pushing back against the current and applying this electric force to that some distance. Okay, so work done per unit charge to move this positive test charge between these 2 points. That's what we're talking about with potential difference. Again, it's measured in volts, which are joules per coulomb. And work is in joules, and our per unit charge would be our coulombs. Okay, so that's potential difference. That's between 2 points that are not on either side of the cell. But the electromotive force, right now we're looking at the difference between 2 points, point 1 and point 2 on either side of my cell. And if I have more than one cell, I have to consider all the cells in this, because the electromotive force is the total energy difference per unit charge. Again, energy per unit charge, so we have joules per coulomb, volts, all the way around the entire circuit. So it's the potential difference when no current flows in the circuit. So they are very linked. The electromotive force is only dependent on our cells and the energy difference between the cells, and it doesn't require a current to flow, whereas a potential difference, right, that it isn't as dependent on the cells, it's dependent on the current flowing between 2 points, right? And usually we have some resistor or some lamp that we're going to measure that potential difference across. Okay, this is one of the trickier parts of this topic, so don't get too hung up on it. Watch some extra videos on this if you want, or just kind of memorize what's here. Okay, next time we're going to talk about resistance, but for now, that's a wrap. Good luck with your homework and school, and hope you guys are doing good. See ya.